Okay, if you didn't already open it up, here is the warm-up question for the day. It's picking up where we left off on Monday, so we've got some code to start. You need to go from code to recurrence, and then from recurrence, plug and chug into master theorem. So go ahead, take 2 minutes, continue to talk about it. We'll talk about it together. TAs, I don't know if any of you are in the room. Feel free to circulate and help anybody out. Awesome. Thanks so much, everyone. Okay, I'm going to guess by the moments of intense focused silence now followed by conversations that we've at least ingested the code on here and we've got some type of start on this. So, like I said, we're going to have to write a recurrence first. Recurrence is that mathematical way to represent a function that has a reference to itself as part of the definition of the function, which is the mathematical version of recursion, where recursion is a method that calls itself, right? So let's start by writing our recurrence. So I always start my recurrences. Please let me write. Just kidding. Has anybody else noticed this bug every single time I go to use my pen for the first time? This is a very reproducible bug. PowerPoint. Okay. Yep. And it's okay, because as I lament PowerPoint, literally today I was trying to find equations in Google Slides. There's no equations in Google Slides. How is this company functioning without equations in one of the most important productivity tools that we create? Okay, let's see. Second time. Okay, there we go. Okay, so we got to write our recurrence first. So I'm going to start with T of n, set it equal to, and then I use my curly brace annotation, and I'm going to write a code model for two different branches of this code. One branch being the non-recursive base case. Maybe I'll make that green. So here's the base case, and that's the stuff that has no recursive method in it whatsoever. So we should be able to code model this like we've been able to code model anything else. So I see that it's got, like a, why? I see that it's got a check and it's got a println. So maybe there's like, I don't know, like +2 between this and this. And then we've got this limitation here, less than or equal to 100. And so I'm just going to directly translate that over into the recurrence. So I'm going to say, you know, like some amount of constant stuff. So I'm just going to say D in this case. And D just stands for some constant number. Maybe you wrote 2. Maybe you wrote 1. Maybe you felt like it was 3. And maybe I could be convinced of that. But some constant. There's no factor of n in the base case. And then I will just say when n is less than or equal to 100. Any questions on how I represented the base case in this recurrence? Then we kind of move on to the recursive case. SE, blah, blah. And we know that we need to model everything, including any work that's happening in addition to the recursive calls. So if I'm kind of looking at this, I see like, okay, maybe here's like a +1. And then I've got a for loop that I see runs 16 times. And inside of that for loop is that dreaded recursive call. And that recursive call contains inside of it how n is going to transform from wherever it starts to down to the base case. So because I'm going to divide by 4, and my base case is any number smaller than 100, I know this is not going to be an infinite loop. I've got a recursive case that will take any number however big, and after some number of iterations will eventually get me down to the base case. But I'm doing this recursive call numerous times. So, does anybody want to offer what they think the code model might be for this recursive branch? Any suggestions? Let's see. All right, the brave front row. What do you got for me? 16 yes. Yes. Absolutely. Plus, yeah. And what did you plus? Yeah, I agree. +1 is exactly what mine is. I am now going to start to use placeholders for the constants in these cases so that we can slowly move away from arguing over if this was 1 or 2 or things like that. But 1 is totally correct. So I'm going to put a little constant here, and I'm going to give it like a subscript, like, oh, that's like some constant. And then this is for any value of n that's not this, so I'll just say like otherwise. And now, can you see that we have a recurrence that looks gosh darn similar to that format of the master theorem? So remember, the big important pieces here, and I think the part that's, you know, less familiar, a little more uncomfortable, is finding A. That's the coefficient. That's how many times the recursive call is called every time. So if there was no loop here, maybe A is 1. If I had 2 calls, one right after each other, the coefficient would be 2, because I'm making 2 recursive calls. If I changed that 16 to 1600, the coefficient would be 1600. The other thing then is finding that B, and thankfully, it made your life easy. It's just directly representing it over. So those are the parts that are probably unfamiliar. They're a little different than the code models we've been writing otherwise. But other than those 2 pieces, everything else here, like this piece, is just code modeling non-recursive stuff. Now, in this case, we have some constant, pretty small number of non-recursive stuff. But for example, if I had a loop after this that ran n times, then maybe my non-recursive work would be +n. If I had a nested loop that did something but didn't make any recursive calls, then I would have +n squared. But I need to make sure that within the recursive case, there is likely always going to be some amount of non-recursive work on top of whatever recursive calls we're going to make. Not always, but just it's the thing that students tend to forget the most often. Any questions on how I got to this recurrence? Okay. Was anybody able to plug and chug and get all the way down to a big theta? Anybody? Anybody figure out at least which category here it fell into? Are we now just going to allow the front row to save us every time, y'all? Shout out to you, front row. I wish I could say I was a front row student in school. But you know what? You hold it together for all of us. Okay, what do we got? Who wants to give it to us?
I got O of n squared.
Oh,
Theta of n squared.
theta, yes. I love how you said that because I'm going to accidentally say it that way almost every time. But yes, keep in mind, master theorem gives you the big theta, which technically means the big O is also n squared and the big omega is n squared as well. But you're absolutely right. It falls into this case. And here is the work so you can see it. So A is 16, B is 4. If you plug and chug into Wolfram Alpha, or maybe you just know enough about algebra to recognize this is on the simpler side of a logarithmic identity, that log base 4 of 16 is 2. The thing that might be also confusing is identifying C. And remember that C is the exponent on the term of n in the non-recursive work. So if we have constant non-recursive work, there is no factor of n, so the exponent of n is then 0, i.e. there is no factor of n in the non-recursive situation. That is specifically why we wanted to do this example, to show you, because a lot of times you will find that C is 0. So we plug and chug, and we recognize 2 is greater than 0. And so when we do all of our math, that tells us that apparently the big theta is n to the exponent of whatever that log base b of a is, which happened to be 2. So you're absolutely correct. We got n squared. There is going to be a question almost identical to this on the exercises that are coming out on Friday. Can I answer any other questions about this before I ask you to do it for some amount of credit? Yeah? Okay. Yeah.
So the C is for base case, and it's the base case when there's only,
So C, and I understand why it's weird, right? So C is in the recursive case, but it's the non-recursive portion of the recursive case. So technically C is literally just coming from this line right now. If it helps, and I would love to answer these questions, if you could imagine, like maybe we had that, and then maybe under here I had something that was like 4, I equals 0, I is less than n, I plus plus, and then maybe I like systemed out dot print something here, and that was also in my recursive case, then my code model would have been 16t n over 4 plus some amount of constant plus n. And that factor of n would have come from this loop, which is not recursive work, but it does exist in the recursive case. And so in this situation, C would have been 1 because the exponent of this n, though we don't write it, is technically 1. If I took it to the next level, and instead of just having a singular loop, I had a second loop that went over n times, and then systemed out.println or something like that, then my non-recursive work that is still in the recursive case would be n squared plus some constant. And in that case, then, C would be 2, because it's that exponent on the term of n. Clarifying questions? Yeah.
But it wouldn't change your big theta.
In this particular situation, if C became 2, then when I come over here, I would actually end up in this case instead of in this case, because if C was 2, then when I came over here, I would have changed that to 2, and I would have then done this check. Hey, log base B of A, that's still log base 4 of 16. None of that changed. But I'm not in this situation anymore. I'm in this one. And so then I would have ended up with apparently n squared log n. Yes. What if fn is log of what? Like what if this piece is log of n? Oh, or what if this piece was log of n? Ah, what an amazing question. Then you might say, well, Casey, that sure doesn't look like this delightful model. It's hard to figure out what's C in that case. And you would have correctly identified that master theorem doesn't work for all recurrences. I know. So historically, I would then spend literally the rest of this lecture taking you through the mathematical solution to find that closed form using something called tree method. And there's a bunch of kind of scary slides in here because I used to teach it every quarter. And this quarter, I decided I'm not going to subject y'all to that math. Your TAs may or may not talk about it tomorrow in section. And based on the time right now, I've decided I'm not even going to talk about it anymore in lecture. So if you are like, Casey, I would love to know the algebraic way to find the closed form of the big theta of a recursive function that doesn't fit into the master theorem, come to office hours. We'll geek out over it. We'll talk about it. But for right now, I'm going to consider that out of the scope of the class. Yeah.
What happens if you evaluate log b of a in the third case of the master theorem and you get like a fractional output? Would that be something that's not covered in the master theorem then?
So as long as it fits in this formula, it counts. So if you got a fraction, that fraction probably would still be greater than 0.
Right.
So it would still fall into this case.
Okay, so if you got theta of n of like 3 halves, for instance, right, would you categorize it as n of 1, so n, or would you categorize it as n of 2?
Wait, sorry, if what? Say that again.
If your log b of a, you evaluate that to be 3 halves,
Sure.
for example,
Mm-hmm.
then and you have a theta, a big theta of n of 3 halves as a fractional exponent, then would that
Oh, you mean like if this piece here came to like 3 over 2?
right,
Oh, okay.
then would that be categorized as linear? Would that be
Oh.
squared? Would that, or would that
It technically is its own exponential class then. Yeah. The exponents all count in that way.
okay.
Yeah. You're going to go over this more in section tomorrow. These will be posted. Ask your TAs tons of questions. Make sure you practice it. I strongly suggest going to section because literally they're going to do exactly this again, and then we're going to give you an assignment on it on Friday. So we're not trying to surprise you or nothing. Just in the interest of time, because we have like actually something. Today we are learning the topic that is, in my opinion, the thing you will use the most from this class for the rest of your life. So I'm like, algebra, hashing. That's what we're going to talk about. Hey, so some quick announcements. So exercise 1, due this Friday, hopefully not a surprise, individual assignment. Project 1, Dex, due today. I really hope that's not a surprise. Project 2 is officially out. Shout out to our wonderful TAs who make sure to get that out for you like early in the morning. They are crushing it. Project 2 is a 2-week assignment. Do not confuse that with a 1-week assignment we have given you 2 weeks to complete. I could say this to you every day, and I will still see y'all because I've decided to take the Wednesday night office hours specifically because, like, I've been there, y'all. You don't have to be embarrassed. I've been in that situation. But I know I'm going to see way more of you 2 weeks from today than I should. Really, please, 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 please start now. Please start now. Because office hours is going to get really quiet between now and next week because everybody else is going to wait to start. And the problem with that is we live not in that delightful frictionless universe, but we live in the confines of physicality. And as you can imagine, I literally just ran from one job to this one, like literally ran. And so I have to end my office hours exactly when I end my office hours. And so I will get through the people that I can get through. That I have told all my TAs, they are also students first. They will get through as many people as they can get through next week. But don't be the person that unfortunately means you can't get your question answered next week when chances are the TAs are going to be sitting around with not a lot to do in office hours this week. Be the early bird, y'all. Get this worm. You want it, okay? But like, for real, please. Okay, I won't vamp this much in futures, but like historically, this has been the particular assignment that people get really hung up on and then wait to the last minute. And then I think this one traumatizes everybody, and then they take my advice from here on out. So like, you know, what is it? Like smart minds learn from themselves, brilliant minds learn from the mistakes of others, whatever. Be brilliant. Also, just FYI, I did tell my TAs, we don't have quite the same strictness of like, we can only answer some things like 1-4X, but we do need to get through people as quickly as we can. So I've told the TAs that they can only spend up to 15 minutes on any given question, and then they have to move on to the next person in line. Sometimes that means that you all don't get to finish your conversation. That means you're just gonna have to get back in the queue. I will also say this here in this moment, I included our offering some online office hours, but for context, we're offering more in-person office hours because we literally can just get through way more people in person. Things go faster in person. We can like address questions as a group. You can work as a group. We actually get through almost twice as many questions in person as we do online, but we have the online office hours because times are weird. And y'all should absolutely be free to stay home or do whatever you need to do to keep yourself and your loved ones safe. So the online office hours are really for that use case, not necessarily as much the I'm lazy and I'm already at home and in my comfy pants and I don't want to come to campus use case, though I feel you, but like, help us help you. Please come in person. Please respect the TA's time limits on things. I told them they can say I'm the bad guy because I will be the bad guy. And obviously the TAs are all delightful and will all try to stay late and help you more than they are signed up to do anyway. But help me help the TAs. Yeah? And also, just so that it's starting to come into your awareness, our simulated midterm is going to go out on Friday, April 29th. You won't have a programming assignment out during that time, so you can focus on the midterm, and we're going to talk a lot more about it as we get close to it. But remember, the midterm is not a timed exam. It's something you will have multiple days to work on, including your notes and the internet and things like that. Any administrative questions? Cool. All right, you guys want to see these scary slides as we just drive on by? So here's the master theorem. Here's more examples. Here's an explanation of why master theorem works. Read it. Here is the merge sort algorithm, and here's the code for it. And here's the recurrence for that code. And here is how you would maybe try to plug and chug it into master theorem. Yay, here's another example. Finally, our third recursive pattern is doubling the input. Maybe that's Fibonacci's number, the most annoyingly common example of recursive code. That literally was my code tech screen question when I got hired as a developer at Microsoft. Literally. I hope they don't do this anymore because I almost laughed. I was like, you mean like the one example everybody uses to teach us recursion? He was like, yeah, that one. I was like, here? So Fibonacci, and this is the one thing I will pause to say, Fibonacci is a mathematical thing, something from nature, maybe? I don't really know what Fibonacci's number is. I'm going to be real with y'all. And the way that you calculate it is that any individual Fibonacci number is the sum of the two Fibonacci numbers preceding it. So it's a great situation for a recursive call. But I wanted to show you this visualization of how you can start to mentally think about how the runtime of recursive calls grow. They kind of end up becoming this exploding tree. So because in this case, we've got one recursive call here, that creates this branch off of the initial call. And then that recursive call creates its own set of branches, and so on and so forth. So it's like this branch here is from this one, and this branch here is from this one. And then it's recursive, right? So like this call is going to have this branch from this guy and this branch from that guy. And so you end up with actually a really quickly growing set of method calls when you're doing something recursively. And so I drew this out so you can start to understand a little bit more about the runtime of recursion, it might help to picture how many method calls are actually getting created. And if you're like, oh, Casey, how do we do the mathematical calculations for what the big O runtime of that is? Well, you could just plug and chug. This is a method called unrolling. That's another way that you could get to the closed form. I think that's the least intuitive way, so this is me totally blowing by it. And then here is all of the math to find the closed form of the recursive thing. And there you go. It was 2 to the n, as it turned out. Maybe I'll post lectures from later quarter or previous quarters if you really want to watch me walk through all the math for that. Here's also some graphs. You can get a general sense of the relative growth rates of these recursive functions. So binary search had that logarithmic runtime. That's like way down here in this context. Merge sort had n log n runtime, so you can see there. And then Fibonacci, that 2n. Man, when we zoom out to large numbers, log n and n log n look identical, right? But that polynomial time, not a fun one. Yeah? Does anybody have any quick questions? Yeah, please.
Do we have to know this for the midterm?
No, you do not have to know this for the midterm. I will admit, in past quarters, my midterm always had a do the tree method question. And like I said, it's mostly just because my bosses used to be like, don't take the math out of 373. And then the pandemic hit and we all stopped doing exams. And now we're back in person. I was like, I wonder if nobody will notice if I just don't really do those old exams anymore. Thanks, pandemic, for some things. Okay, here's what I really wanted to talk about today. We're going to spend today and tomorrow, and I believe Monday, talking about it. Like I said, it's actually a bit of a meme that this is the most useful thing you're going to learn in this class. In fact, the meme is, in an interview, when you don't know the answer's just hash it. Why is that the answer? So let's return now that we have all these fancy mathematical things to analyze code. We're officially starting off on our journey of collecting ADTs and data structures that we're then going to use those tools to analyze. So taking you way back to week 1, we remembered this ADT called a map. You might have seen it looking something like this in 143, where you had like map of some type to another type. And then you had hash map and tree map, or 2 different data structure implementations of the map ADT. Data structure. And so today we're going to learn all about what the frickety frack that piece is. I am going to stop referring to this thing now as maps and entirely refer to it as dictionaries from here on out. They are the exact same thing. What the heck is this thing? So it is this idea that we have a collection of items. They are not ordered. They're in this blob, okay? They're not ordered because when you put something into this collection, I don't maintain the order that you gave it to me in. I'm not maintaining some queuing system or some chronological order. Instead, I am trying to optimize for lookup. And if you think about a dictionary, that's what a dictionary is, right? You have a key, which in the dictionary case is a singular word, and then you have the value. And the value in the dictionary context is the definition of that word. So if I wanted to open up that book and look for the definition of something, I would use the key, the word, to navigate through that dictionary in alphabetical order. The key unlocks the thing I'm looking for, the value. The key operations, put, it takes in a key and a value, and it adds one of these delightful entries to our collection. Get takes a key and spits back out the value. Contains key tells me, is that key already in the dictionary? Because dictionaries require unique keys. You cannot have duplicate keys in a dictionary. And as we get deeper into it, you'll be like, oh yeah, because that would just totally destroy everything. And so it's a functional design of the ADT to make the implementation work. So unique values for keys. And then you can remove a key. So I think I also blew through these in the first week of class. You can implement a map using an array where each bucket of the array holds those key value pairs. So this little item inside of here, maybe that's its own type of object, and that object type is called a pair. So maybe somebody else has written this, and then you've got an array of pair objects. And so if I wanted to call contains key of C, the way that this would work is I'd come in and I'd look at the first bucket and I'd be like, hey, is your key C? It's not. Hey, is your key C? It's not. Hey, is your key C? Heck yes, it is. Great, return. If I call get, I'm saying, hey, go get me the value associated with the key D. I'd come in and I'd be like, hey, is your key D? No, no, no. Oh, sweet, I found it. Return back the 4. If I asked to put B in, I'd have to go in and check, does B already exist in this collection? So I have to look through everything. And in this case, it does exist. So I would go in and then I would just replace the previous value with whatever the new value is. So put can erase a previous entry by replacing the value if you put with a key that's already in the dictionary. And then you can also put, you have to add in something new, but in order to add in something new, I have to look at everything and decide whether or not that thing is already in the list. Because anytime I'm adding to the list, I'm asking myself, am I transforming a value or I'm adding a whole new entry? This underlying array structure, I still have to loop linearly over it because I don't know which key is in which bucket. They're just sort of added linearly as I fill up the array. And as you can imagine, if I tried to put anything else into this array, what would have to happen in my array map implementation? Yes, we would. It's the same thing that happened in the array list. Same thing that happens in array queue and array stack when we run out of room. What do we got to do when we run out of room in the underlying array? Yes, make a new one, double the size, copy everything over. Same situation. So if you look at the runtimes of this, here what we've got is we've got the worst case up here, which is if the key is the last thing to look at, or it's just not in the dictionary, meaning I have to look at absolutely everything, or the best case, which is like, hey, the thing I was looking for happened to be right at the beginning. In this case, you might be like, Casey, that best case scenario sounds like pretty rare. I would agree with you, and I would say in this situation, most people are not going to care about the best case scenario. They're going to just assume that's probably not going to happen. We got to just assume the worst case scenario is much more likely to occur, and I need to plan against that. I'm going to continue to show you the difference between best case and worst case, but that's an example of why industry is so particularly obsessed with worst case, because a lot of times too, it's like that best case is just kind of unlikely. But it does help us get a sense of what's happening here. You could do the same thing with nodes. So you could have a linked map. But a linked map, that's a situation where we don't have to incur the growth factor, but I still don't know which node holds the key I'm looking for. So anytime I'm looking for a key, I still have to go through and kind of look at every single node until either I determine the thing's not there or I find the thing I'm looking for. So when we look at the runtimes, okay, I did some animations, there you go, they end up being identical. And like I said, the thing about the map, the dictionary ADT, is I'm trying to optimize for lookup. And this is just really not optimized for lookup, right? Arrays and linked lists, they tend to be pretty optimized for order. You know, they're kind of maintaining the order in which you add things. And I already told you in the map situation, I don't care about the order. I care about being able to find the thing I'm looking for. I don't care which word is most recently added to the dictionary, right? I just need to be able to find the thing I'm looking for. So can we do better? So we could think about how to simplify the problem. Maybe there's some simpler solutions, some more efficient solutions if we put some constraints around what we are able to do with this thing. And you'll see this is a common approach to design where we're like, okay, well, instead of trying to boil the ocean, we're going to take this one sip of water at a time. That's kind of what we're doing here. And we're going to build this design up piece by piece. So the thing we're going to simplify here is we're going to say, okay, well, like arrays, they kind of come with their own lookup value, right? Like they come with the index. And that previous array map implementation, it didn't pay any attention to which key was associated with which index, right? Just sort of like threw that information away. Maybe I can leverage that information because arrays themselves have that constant lookup, right? Like I can jump right into the array at index 3 and get what I'm looking for. So what if we make this simplification where we say, okay, we're only supporting integer keys. And if that's the case, then we can come up with this idea of a direct access map where, well, then let's just make sure that whenever we put something into the map, we've already decided we're only taking integer key values. Let's put it at the index that matches its key. So that if I come back and I say, hey, okay, put Sherdil into my dictionary with the associated key of 3, put that at index 3. So when I come back and I ask to get it, I don't need to loop and look for it. I just jump right in, pull that straight out. Here is literally the code in order to accomplish this. And you can see what we end up doing then is we end up needing to kind of like just use key as the index of the array that we're accessing. Great. Looks really nice and simple code, right? But your brain might already be like, yo, Casey, this is such a limited use case. But look at that runtime, y'all. Oh, it's so beautiful. This is the dream, I say. So we may have simplified our problem, but we've gotten to the ideal runtime. This is it. This is perfect runtime. We can't do any better than this. Constant time everything. It doesn't matter if you have 1 billion items or 10 items. It all just is this instantaneous sort of lookup. Now we're going to try and build back up this design in ways that make it more flexible. But each time we add in that flexibility, we'll review the runtime that is sort of added on. So it's like we kind of like reduce down to our frictionless ideal situation, and now we can intelligently build back up into the design to make something a little more flexible than the direct access map. So, for example, some of the things that may be in your head already is, okay, well, that sounds like a lot of wasted space, because if I want to, say, accommodate int values, I need to make an array that is at least the size of my largest int value. And like, what if, for example, my int values were your student numbers? Your student numbers are like 6 numbers long or something, right? I would have to make some massive array so that I could get all of those wonderful student number values, but I would know I'm never going to use the first, 99,000 spaces of the array, because I had to make this massive array just to get indices that match my current key set. So that's weird. That sounds like a bunch of wasted space. That's not a good time. Also, only integer keys. How often is that really coming up, right? In our dictionary example, we had words. We could use a key of any object type, strings, ints, pairs themselves. You could have a map of maps, as it turns out, right? So that's not particularly useful, but the good thing, super fast. Great. Very, very small amount of code to implement. So how do we start to improve upon these two limitations? Maybe we want to talk about, instead of just going from like this was the verbatim integer to this verbatim index, maybe we want a way to kind of like translate the ints to a number that we know is going to fit in our array. What do I mean by this? So, like I said, idea 1, if we could do this for any integer, we'd have to create a giant array with every single integer as an index. So can we even allocate an array big enough? Gosh, that's super wasteful. Okay, apparently the animations are out of order. The idea too, instead, create a smaller array, but create a way to sort of translate between those big numbers and smaller numbers in the array that we know are actual indices. So instead of making such a massive array to get to your 6-digit student numbers, maybe we have some type of math that we can do that sort of maps that large number to a number that's smaller. So we're not wasting all of those like smaller value indices spaces. So there's the animation I was looking for. The giant array, that's where we had like, these are all of our possible integer values, and they're just going straight directly over to that space in the array that has that index. So there's a bunch of wasted space. But this step, this adds this moment of translation, this intermediary where I take the key that you've given me and I map it to somewhere in my array that I know will actually fit. And I know it doesn't seem massively, life-changingly transformational at this exact moment, but this here, that's it, y'all. That is the hash. This is the thing that has literally transformed all of computer science and answers so many of your interview questions. This idea of how we figure out an efficient way to take in a key and then find a specific location in our array where it will live. And I'm going to talk for the next 3 lectures about how we do that thing. Okay. So, hash function definition. A hash function is a function or method, whatever you want to call them, that can be used to map data of an arbitrary size, and as we will eventually find out, arbitrary type, to some fixed size integer value. So far, the way we've been talking about is we're all living in int land. How do we go from your student number? Like, let's say we're making a hash table, which is the thing we're making together now, of all of you. There's 310 of you in this class. It would be gosh darn waste to make a array that's millions long. I want to make an array that's maybe 300 or 500 long, and then I want to figure out how to translate your student numbers to some index in that array, knowing that that array is only going to have, what did I say, 300, is its max index, or 500 is max index, deciding how big you want it to be. So, the simplest way to do this, and in fact, the hilariously most common way, and actually was my answer to an interview question, I think at like my last round at Google once upon a time, was, what's a good hash function for integers? Where is it? I want to highlight the sentence of it. It is just literally like mod by table size. This is a reminder on how mod works. It's the remainder operator. So if I had the number 14 and I modded it by 4, 4 fits in 3 times with a remainder of 2. And so the mod of 14 mod 4 is 2. Here, I think much more interestingly, is examples of how freaking useful this operator is. Anything mod 10 is going to spit out the last digit. 101 mod 10 is 100 divided by 10, which is 100, and the remainder is 1. So modding anything by 10 is going to give me the last digit. You can check whether something's even or odd. If I mod by 2 and I get a remainder of 0, that means that number is perfectly divisible by 2. It's an even number. Great. Or, and this is what we're going to actually be using it for, you could limit integers to a specific range. So if you mod by how big that range is, it will find you a remainder that then is some number that fits in that range. Because the remainder could only ever be the range minus 1, right? Like, if I modded something by 10, the largest remainder I could ever get back is 9. Because if I got back 10, then like that fits in perfectly, right? So, yes, limit keys to indices within the array. Great. Oh my gosh, I've made this timing happen. Okay. Ugh, those stupid animations. Why are they so bad? Okay. Let's create a hash table for the first time. Let's put in, with the key of 0, the value of foo. 0 mod 10, 0. Boom, there's foo right there. Let's put in 5, or let's put in Baz with the key of 5. 5 mod 10? Well, 5 doesn't fit into 10, so the remainder's 5. Boom, looking good. Let's put 11, a number that does not exist in the current set of indices in this array, but 11 mod 10, that remainder is 1. And so now Biz goes right here. Yes?
What if we have two numbers that have the same movement?
Oh, it is literally 320, and that question is what we are going to spend all of lecture on Friday talking about. What happens if two things hash to the same bucket? What do we do? Great question. There you can see how it works out. Thanks so much, everybody, for your patience with everything. Please do go to section tomorrow. Like I said, it's going to be very useful for your exercise. Get started on Project 2. I believe in you.